Hello, today I'm going to be talking about different ways of representing motion that you can use in physics. There are 4 ways that I'm going to describe today. There's probably more, but these are the 4 that I could come up with. We have graphically, mathematically, diagrammatically, which I swear is a real word, and descriptively. Descriptively is just the way that we use language on an everyday basis. For example, this might be an experiment that you can carry out in physics class, or just what you do fooling around with your toy cars. Here we have a toy car that starts at a position of 4 meters and travels towards the origin, and that's just wherever you decided here there be 0, at a speed of 0.3 meters per second. So we could graph this, and we could plot the motion of where that car is with respect to when that car is there. And we'd end up with a plot that looks very similar to this one. And this does a lot more than just show where the car is at a given time. We can take a look at the slope, and remember that the slope of a graph represents the change in that line. And the velocity is the change in position. So the slope of this graph represents the velocity of the cart. We can also look at the y-intercept, and the y-intercept represents the location that that cart started from. You can see that I asked Excel to give the line a best fit, so its position along the x-axis is equal to that negative 0.3 meters per second. It's negative because it's changing towards 0, getting smaller and smaller at that 0.3 meters per second, times the time plus that initial starting position of 4 meters. And this translates quite nicely into the segue of we can diagram this mathematically. We can represent this mathematically. And so we have our first equation. Position, in this case along the x-axis, equals velocity times time plus the initial starting position. And if I include the data that we had over on the previous slide, we could see that it fits quite nicely. We have x equals that negative 0.3 meters per second, that's our velocity, times the time plus our initial starting position. Now you could be looking up there and going, out there, and going, hey, what's that funky arrow doing over that velocity? Well, that shows that velocity is a vector. And there was no greater gift to physics teachers than when DreamWorks made Despicable Me.
I'm applying for a new film loan. Go by the name of Vector. That's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check the weapon. Piranha! Oh yes! Fires that I've put on. I've never seen one before. Now you have my invention. You have demonstration. Oh! Ow! It's so difficult sometimes to get on that side.
So there's a couple important things out of that video. The first is that if you are trying to invent a weapon, make sure it is at least as dangerous to your enemy as it is to you. The piranha gun fails this very basic test. Second is, if you are going into any field of villainry, do not wear an orange jumpsuit like you just escaped from San Quentin. This is what we call a poor choice of fashion. And third is that a vector is a mathematical quantity that represents both direction and magnitude. I can't pull off the rest of that, but this is very important because if I said that I was driving at 35 miles an hour, you have no idea which direction I was going. If I were to give you my velocity was 35 miles an hour east, now you know both where I am going or the direction at least, and the how fast I am getting there. So velocity is a vector, speed is not a vector. That would just be the 35 miles an hour. And the fancy 10-penny math vocabulary term for that is a scalar. So average velocity, that's going to be displacement over time. And displacement's just the final position minus the initial position. So here we have velocity, again, with the vector arrow, equals displacement with the vector arrow over time. And displacement is that final position minus the initial position. And so this gives us a really good idea of what's going on. Also, you can notice that if you were to replace the displacement in that velocity equation up there, you could then rearrange that to get that first equation that I showed. And speed is just the distance over time. Distance is the however long that path you take in order to get to wherever you're going. So a prime example of this is this morning I went for a 2-kilometer walk. I went down to the park, I walked around the park, I came home. My watch told me my average speed was 1.5 meters per second because the distance that I went was 2 kilometers. The time was about 25 minutes. But the displacement, that's my starting position minus my initial position. Well, or my final position minus my initial position. My final position was the same as my initial position. So my displacement was 0. So my average velocity was 0. And this can get a little bit confusing for some people because we're used to being able to talk about, hey, speed. Speed is just that distance over time. There's also going to be talk about instantaneous velocity. And that's if I was walking this way, my instantaneous velocity might be 1.5 meters per second. And that's going, well, it might be 1.5 meters per second west because we need to include that direction information, don't we? So this gives you an idea of different ways that we can talk about motion in the mathematical terms. We can also use diagrams, and the diagrams that we're going to use are called motion maps. And each one of these dots represents where the object is at a given time interval. So one of the things that's going to be very important when dealing with this is that you are going to want to label all of these points. Because if you start counting, usually you start counting at 1. But with motion maps, you want to start counting at 0 because that first dot represents where we are at 0 seconds. So it is very, very important to label those so you don't end up making mistakes. So we have 0, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can see how our position changes from being at 4 meters at 0 seconds all the way to being at 1.3 meters at 9 seconds. So here we have traveled 2.7 meters in the negative direction over that 9-second period. And for those of you that remember the graph on a couple of slides back, this is the same motion. We started at 4 meters at 0 seconds. We traveled at negative 0.3 meters every second, and this is our result. So let's do another example. So here we have a same cart, but the cart is starting at a position of 2 meters and moves at negative 0.5 meters per second for 6 seconds. Runs into your lab partner's foot and stays there for 2 seconds while they bend over, pick it up, turn it around, and then it goes at a positive 1 meter per second for another 2 seconds. So let's deal with the diagram first. Let's deal with that motion map. So at 0 seconds, we are sitting here at 2 meters, and we have a velocity of negative 0.5 meters per second. So I'm going to draw my arrow in the negative direction, and I'm going to draw it like this. You'll notice that I'm drawing the arrows relatively short in order to make sure that I have room to draw and it doesn't look too messy. So at 1 second, we're now sitting at 0.5 meters. We're still going at negative 0.5 meters per second. So I'm going to draw the same arrow, and I can do the exact same thing for 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, and now at 6 seconds we are no longer moving. So now we have stopped, and that is why I don't have an arrow. At 7 seconds, we haven't moved anywhere. We're still sitting at that negative 1 meter position. So that's why I drew the dot right underneath the 6. I could have drawn it over the top. It really doesn't matter. At 8 seconds, we're still in the same location, but now we're moving at a positive 1 meter per second. So I'm going to draw my arrow in the positive direction. And because we're going now twice as fast, I'm going to draw my arrow twice as big. And I can continue that for 9 seconds. And I can continue that at 10 seconds. Now, at this point, we're done. And we don't know whether that cart is going to continue moving or not, so we can either leave it with that arrow or we can get rid of it. It really doesn't matter at the end of the day. So now let's look at this graphically. So same idea, same cart, same motion, but now we're going to graph it. And our position graph is going to look a lot like this. So here you can see that we're starting at 2 meters. For the first 6-second period of time, we're going in the negative direction at 0.5 meters per second. So every second, our position is decreasing by 0.5 meters. So we got 2, we got 1.5, we got 1 meter, we got 0.5 meters. Now we're at the origin, our 0 point at 4 seconds. Then we're continuing into the negatives at negative 0.5 at 5 seconds. And then at 6, we've now ran into the lab partner's foot at the position negative 1. We're now sitting there for 2 seconds, and then the lab partners now turned it around, and we're going in the positive direction for 2 seconds, ending up at 1 meter. And you can see how this directly relates to the motion map that we drew on the previous slide. So this is a position graph. We can also show a velocity graph. So this is how that velocity is changing with time. For that first 6 seconds, we are sitting right there at negative 0.5 seconds. Between 6 and 8 seconds, our cart is just not moving. So it's at 0 meters per second, our velocity is 0. And then for the last 2 seconds, our velocity is positive 1. So we're moving in the positive direction at 1 meter per second. You might recall at the beginning of this how I talked about how the slope of that position graph shows the velocity, and we can see that looking up at the position graph, we can see that the slope for those first 6 seconds is negative 0.5 meters per second, which is the same as the value of the velocity graph. So we now have several different ways of describing motion. We can describe it with words, we can describe it with math, we can describe it with position graphs, we can describe it with velocity graphs, and we just can describe it with diagrams. Thank you very much, and have yourself a wonderful day.